Okay, picture this. You're walking through a brand new neighborhood during an absolute pouring downpour, and you kind of have to wonder, how does this whole place not just wash right away? Well, in this explainer, we're diving into exactly that, the hidden civil engineering that literally protects our urban developments from extreme weather. We're going to unpack the fascinating data behind the Farley Investigation Area stormwater management analysis. And honestly, this isn't just about pipes and puddles. It's about high-stakes environmental management that literally shapes the ground beneath our feet.
So we're looking at a massive collision here between nature and human development. Think about it. What actually happens when a huge expanse of natural, absorbent land suddenly gets paved over, right at the exact moment a massive 100-year storm hits? I mean, without human intervention, that is just a recipe for absolute disaster. It's a really thrilling problem, actually, and seeing how engineers mathematically and physically solve it is nothing short of incredible.
Okay, let's dive into this. Just wrap your head around the sheer scale of this canvas. 1.73 million square meters. According to the report, that's a 173-hectare zone known as the Farley Investigation Area. Now imagine all that open grass, the dirt, the natural vegetation. Under normal circumstances, when it rains, that land acts like a giant natural sponge, right? It absorbs the rainfall slowly, deliberately, and safely. But the moment we build roads, lay down concrete foundations, and pave driveways, well, we effectively seal off that sponge completely.
And that brings us to a massively rising flood threat. You see, when you remove the Earth's natural ability to absorb water, regular rainfall doesn't just sink into the ground anymore, it runs off. And as it rushes across miles and miles of slick new pavement, it gathers both volume and momentum, rapidly turning into a highly destructive force. That water has to go somewhere, and it goes there incredibly fast.
Let's actually look at the data that proves just how severe this threat is. According to the XP Raft's hydrological model, watch what happens during a standard one-year storm event. Before any development, the peak water flow is a pretty manageable 1.84 cubic meters per second. But post-development, if we don't do anything about it, it skyrockets to 5.23. That is almost triple the volume of water rushing through. And for a 10-year storm, we jump from about 6.8 up to nearly 14 cubic meters per second. Honestly, that's enough rapid water displacement to overwhelm your standard drainage ditch and send aggressive floodwaters creeping right up into streets and people's properties.
But what's really terrifying is the 100-year storm scenario. We're talking about a sudden, massive spike to over 26.5 cubic meters per second. If left unmitigated, a severe storm like that would unleash an absolute wall of water, totally dwarfing the natural pre-development flow of around 15.6. But through some highly calculated engineering, that mitigated flow is actually brought safely back down to 15.22, which is slightly below the original baseline. So how on earth did they pull off an incredible save like that?
Well, the answer is what civil engineers officially call detention basins. But to keep it simple and easy to visualize, I like to just call it the giant bathtub solution. See, when you have a sudden, extreme volume of water rushing off all that new concrete, you desperately need somewhere for it to go. You need a holding zone where it can sit safely while the downstream drainage system catches up. You essentially need to build a giant bathtub to catch the runoff before it completely destroys everything below it.
The Stormwater report outlines two of these primary bathtubs designed specifically for the Farley area. First, we have the Southern Catchment Basin, boasting an active detention volume of 16,500 cubic meters. It is massive. Then, you have the Alpen Lane Culvert Basin, a smaller but equally vital basin holding 4,600 cubic meters. Now, you might be wondering, why the massive difference in size? Well, it's because they have entirely different jobs. The Alpen Basin acts kind of like a targeted bodyguard. Its specific structural role is to hold back just enough water to ensure the existing culvert under Alpen Lane doesn't get overwhelmed and literally wash the road away. The Southern Basin, on the other hand, is the real heavy lifter for the entire primary southern catchment area.
And this brilliantly illustrates the sheer elegance of modern civil engineering. The Southern Catchment Basin isn't just a big, dumb hole in the ground. It features a highly conceptualized two-stage dual drain system. Think about it. You don't want your giant bathtub draining the exact same way during a gentle afternoon drizzle as it does during a catastrophic flood, right? So engineers designed a low-flow pipe to slowly and steadily bleed off water from those minor, everyday one-year storms. But when that massive 100-year storm hits and the water level inside the basin rises dramatically, a much wider weir kicks into action near the top. That allows for a safe, controlled, high-volume release of that massive 16,500 cubic meter reserve.
Now, managing the sheer total volume of water is really only half the battle here. If you just dump water out of a basin, even in a highly controlled way, it can still completely tear apart the physical landscape if it's moving too fast. So we have to logically shift our focus from managing the total volume to controlling the velocity. Basically, we need to tame the incredibly dangerous, fast-moving waters.
To really grasp this, we can look at simulations from the one-dimensional Heck-Ras hydraulic model, which maps out exactly how fast the water travels. Down in the flat floodways, water moves at a relatively calm 0.4 to 1.2 meters per second. To put that into perspective, that's roughly the speed of a leisurely walk. But here's the danger zone. Once water hits 1.5 meters per second, it hits the threshold for scour. Scour is when water is moving so fast it literally rips the soil and vegetation right out of the ground. And the model predicts that at choke points or steep transitions, like approaching the main railway culvert, speeds will reach up to 2.1 meters per second. That is a high-velocity physical threat that would quickly erode a channel into absolutely nothing.
So what's the solution to these aggressive 2.1 meter per second flows? It's something called riprap. It's kind of a fun word, but it serves a really vital, heavy-duty purpose. Riprap is essentially heavy rock armor. Engineers take these heavy rocks and embed them specifically into those vulnerable, high-slope choke points. By lining these exact channel zones with heavy rock, they create a heavy friction barrier. That barrier slows things down and completely prevents the high-velocity water from causing that devastating localized scour and erosion.
So the absolutely crucial point here is how beautifully all these individual engineering pieces fit together into one comprehensive storm defense strategy. Step 1, we capture the massive runoff volume from the new concrete right inside our giant detention basin bathtubs. Step 2, we regulate the release of that captured water using those brilliant two-stage outlets, gracefully handling both everyday drizzles and massive downpours. And finally, step 3, we armor the vulnerable choke points downstream with heavy riprap so that fast-moving water can't just tear the earth apart. These 3 steps perfectly combine to neutralize the 100-year storm threat, bringing that terrifying 26 cubic meters per second back down to a safe, normal baseline.
It's truly fascinating, isn't it? Just how much invisible, highly calculated work goes into keeping our urban spaces dry and safe. We pave over nature for sure, but through smart engineering, we can flawlessly mimic nature's original drainage system. So I leave you with this final thought. The next time a 100-year storm hits and you're just watching the rain pour down from the safety of your window, will you be able to recognize the hidden engineering that's actively safeguarding your community? Keep looking closely at the world around you.